You are listening to Sales Optex. Visit us at salesoptex.com.
Imagine watching a multi-million-dollar data warehouse completely crash. Like, just taking the company's executive dashboards offline for a week.
Oh, man.
Yeah.
The absolute worst case scenario.
Right. The CEO is furious, the data engineers are just scrambling, the panic is palpable, and when they finally do the postmortem, they discover the culprit wasn't, a malicious hack or a massive hardware failure.
And never is.
No, it was a third-party sauce vendor deciding to add a single tiny new field. Let's say it's like a secondary shipping address in their API. That one new field ripples through the architecture, breaks the extraction code, corrupts the dimension tables, and basically brings the entire enterprise analytics operation to its knees.
It sounds totally hyperbolic, but I mean, anyone who has spent any time in data engineering knows that exact scenario is playing out somewhere in the corporate world at this very second.
Oh, absolutely.
You pull out one block, or in this case, a vendor tweaks a data type from an integer to a string, and the whole Jenga tower just comes crashing down.
The Jenga tower. I mean, that is the perfect visual for this. We sort of treat data like it's this precision-engineered utility, right? Where information just flows smoothly from point A to point B.
Right, in a perfect world.
But the reality of modern business data is absolute, unrelenting chaos. You've got dozens of cloud applications, legacy on-prem systems, external feeds, and they are all constantly mutating.
Constantly.
So today, we are going deep into a strategy designed specifically to escape that fragility. We are unpacking data vault modeling. And for you listening, I just want to be clear right up front, this isn't just a dry conversation about database administration.
No, not at all.
We are dissecting a fundamental philosophy for building an architecture that doesn't just survive enterprise chaos, but actually thrives on it.
Yeah, because it requires a complete rewiring of how we even think about storing information. And to do this properly, we've synthesized a massive stack of materials today. Architectural blueprints, implementation breakdowns, philosophical frameworks.
We've got a lot to cover.
We do. We're looking at the core principles laid down by people like Dan Lindstedt, who created the methodology, and insights from Neil Strange. Plus modern engineering guides from Oval Edge, Studio, Warescape, Business Thinking, and Unit 8 that show how this actually functions inside massive cloud environments today.
So I want to start at the breaking point, because understanding the cure requires understanding the disease, The traditional architectures we use, the ones that literally collapse when a vendor changes an API, where did they come from and why are they so brittle?
Well, to understand that, we actually have to rewind to the early 2000s, looking at the origins of Data Vault inside the U.S. Department of Defense.
DoD.
Yeah, the DoD. Picture the scale of that. You have dozens of different intelligence and operational agencies.
Yeah.
And each agency is running completely different legacy mainframe systems built by different contractors in completely different decades.
And I'm guessing none of them were designed to talk to each other.
Oh, not even remotely. And furthermore, these systems were constantly being replaced or updated. But overlying all of this chaos, you have the most stringent, non-negotiable audit requirements on the planet.
Right, because it's national security.
Exactly. When you're dealing with national security or, massive defense budgets, you have to know exactly where every single piece of data originated, what time it arrived, and what it looked like before any analyst ever touched it.
So it's an integration nightmare on a scale most private companies can't even fathom. Why couldn't they just use the standard data warehouse models that everyone else was using at the time?
Because the two dominant models of the era, which frankly are still the dominant models today, they were structurally incapable of handling that specific combination of high-velocity change and strict auditability.
Okay, let's look at those.
Sure, let's look at the first camp, the INMON approach, usually called the third normal form, or 3NF.
Let's break down 3NF for a second. If I'm trying to visualize a third normal form enterprise warehouse, I'm picturing an incredibly strict centralized system where redundancy is essentially outlawed, right?
It's the defining characteristics, yeah. In an INMON warehouse, a single piece of business data, say a customer's primary phone number, lives in exactly one place.
Just one table.
Right. The entire enterprise must agree on what a customer is, what a phone number is, and how they relate. It provides this beautiful, pristine enterprise consistency.
But building that consensus sounds like a political nightmare. I mean, I can imagine trying to get the marketing department, the finance department, and the logistics team to all actually agree on the definition of a customer.
Good luck with that.
Right. Marketing thinks a customer is anyone who downloaded a white paper. Finance thinks a customer is someone with a cleared invoice.
And that political nightmare translates directly into a massive development bottleneck. It can literally take years to model a true 3NF enterprise warehouse. But the fatal flaw, especially for something like the DoD, is that an Inman model assumes you have total control over your source systems.
Oh, I see.
It assumes you can just force the upstream systems to conform to your pristine enterprise model.
Which is a complete fantasy in the modern world. I mean, you don't control the data model of your Salesforce instance or your Workday HR system.
Exactly.
They push a sauce update, the shape of the data changes, and your rigid 3NF model just shatters because it cannot accommodate the unapproved redundancy or the new relationships.
Exactly. So if Inman's too rigid, the industry often swings to the other extreme, which is the Kimball methodology, famous for the STAR schema.
Right, the STAR schema. That is what business intelligence tools absolutely love. It's what most analysts think of when they hear data warehouse.
Yeah, it's the classic.
You have a massive fact table in the middle, like every sales transaction ever made, and it's surrounded by dimension tables that provide the context, the customer dimension, the product dimension, the time dimension.
It looks like a star, hence the name.
Yeah.
And for querying, it is brilliantly fast. Business users can easily drag and drop fields in a dashboard because all the data is pre-joined and optimized for their specific questions.
So where does the STAR schema fail then? If it's so fast and user-friendly, why was it failing the DoD, and why does it fail large enterprises today?
Because a STAR schema assumes a relatively stable business environment. The dimension tables like your customer or product tables are highly curated. If a source system changes its schema, or if the business decides to categorize products in a completely new hierarchical way, you have to physically re-engineer those dimension tables.
Let's walk through the actual mechanics of that pain. If I have a product dimension, and suddenly the business introduces a new classification, say, we are now selling digital subscriptions alongside physical goods, I can't just shove that into the existing table if the columns don't align, right?
You can't. You have to alter the table structure itself. That means you have to update your ETL code.
Yeah.
The scripts that extract, transform, and load the data.
Which takes time.
It does. And you have to backfill historical data if possible.
Yeah.
And most dangerously, you have to regression test every single downstream report and dashboard to ensure you didn't break existing metrics.
Oh, wow. So a tiny change upstream triggers a massive, labor-intensive ripple effect downstream.
It's the Jenga tower again. Kimball is fast for the reader, but incredibly brittle for the builder. So, facing the DoD's chaos, neither rigid Inman nor brittle Kimball was going to work. The architect needed a completely different paradigm.
Which is how Data Vault was born. But before we deconstruct the architecture itself, we kind of have to clear the fog a bit. Because if you look at modern data engineering discussions, the jargon is suffocating.
Oh, it's overwhelming.
You have people passionately debating on forums like, should we build a data vault, or should we transition to a medallion architecture, or should we just adopt a data mesh?
I see those debates constantly, and they always feel like people are arguing over whether they should use a hammer, a blueprint, or a construction permit. I mean, they aren't even in the same category of things.
Exactly. That is precisely the issue. So let's clear this up for you listening. These are not competing concepts, right? They solve completely different vectors of the data problem.
Right. Let's start by defining Data Vault, just to anchor it. Data Vault is a structural modeling methodology. It is the actual physical blueprint for how you design database tables, how you define primary keys, and how you draw the relationships between them to absorb structural change.
The blueprint and the plumbing. Got it. So if Data Vault is the plumbing, what is a medallion architecture? Because every time a company adopts a modern cloud data lake, especially with platforms like Databricks, they start talking about bronze, silver, and gold layers.
Yeah, so medallion architecture is just a data classification and quality framework. It is fundamentally just a set of logical zones.
Okay, logical zones.
Your bronze layer is raw data ingested directly from the source. It's dirty, it has duplicates, but it's a complete record. Your silver layer is where you've cleaned, standardized, and integrated that data. And the gold layer is the highly refined, aggregated data built specifically for a business dashboard.
Okay, so medallion tells me the quality of the data. Bronze is dirty, gold is pristine. But it doesn't tell me how to physically build the tables inside those layers.
Exactly. A medallion architecture doesn't care if you use a star schema, 3NF, or a data vault inside the silver layer. It's just a label. In fact, many of the most robust enterprise architectures use Data Vault as the physical model for their silver layer. The concepts are entirely complementary.
That immediately resolves a lot of confusion. But then you throw data mesh into the mix. Where does that fit?
Data mesh is the biggest paradigm shift, but it has almost nothing to do with database tables. Data mesh is a socio-technical organizational strategy.
Socio-technical, meaning it's about corporate org charts and human behavior, not SQL code.
Yes. Historically, companies had one centralized data engineering team. Every department, sales, HR, logistics, would throw their messy data over the wall to this central team and basically beg them to build a dashboard.
Right, I've lived that.
And the central team becomes an incredible bottleneck. They don't understand the nuances of HR data, but they are forced to manage it.
So data mesh says stop centralizing.
Right. Data mesh proposes that domains should own their own data as a product. The HR department should have its own data engineers. They understand their data best, so they should clean it, model it, and publish it as a trustworthy product for the rest of the company to consume.
So let me synthesize this to make sure the mental model is bulletproof here. Data mesh is the organizational decision that the HR department is going to act as an independent data provider.
Yes.
Medallion architecture is the HR team labeling their data products as bronze, silver, or gold so people know how much to trust them. And Data Vault is the structural engineering they use to actually build that silver layer so it doesn't break every time the HR software gets an update.
That is a flawless synthesis. When you untangle the buzzwords, you realize you don't have to choose between them at all. You can use all three.
Okay, the fog is lifted. Now I want to get to the core claim of Data Vault, that it absorbs structural change without breaking. I need a visceral, real-world example of how traditional models fail where Data Vault succeeds.
The ultimate test of any data architecture is a corporate merger. Let's imagine a scenario where a massive regional bank, let's call them Bank Alpha, acquires a competitor, Bank Beta.
Oh boy. The IT integration for a bank merger is notoriously agonizing. You have two completely different parallel universes colliding.
Precisely. Let's look at the most foundational concept, which is the customer. Bank Alpha, your original system, has always used Social Security numbers as the primary identifier in their database. It's a legacy decision, but it's deeply embedded in every single table.
Okay, Alpha relies on SSNs. What about Beta?
Bank Beta, the company you just bought, modernized a few years ago. They realized SSNs are a privacy nightmare, so their systems generate completely arbitrary internal alphanumeric account IDs to identify customers.
So you have two completely different mathematical foundations for the exact same human concept.
Exactly. Now, imagine you are the data architect tasked with merging these systems into a Kimball star schema. You have a customer dimension table. You have to declare a primary key for that table. What do you choose?
Well, I'm forced to pick one reality, right? If I choose SSN to match our legacy system, I now have a massive problem with Bank Beta's data.
A catastrophic problem.
Yeah.
You have to write incredibly complex, fragile ETL pipelines to intercept all of Bank Beta's data, query some external system to try and find the matching SSNs for their alphanumeric IDs, and somehow map them over.
And if Bank Beta has customers where the SSN wasn't recorded? Or what if it's a foreign national who doesn't even have one?
The pipeline breaks. The row errors out and goes into a dead letter queue. The data never makes it into the dimension table. You are literally losing corporate data because your structural model is too rigid to accommodate a different perspective of reality.
That's terrible.
You'd spend 6 months writing exception logic just to get the dashboards to turn back on.
It's a nightmare. So how does Data Vault approach this exact same bank merger? How does it avoid forcing that choice?
It avoids the choice through extreme structural separation. And this is where we have to deconstruct the vault into its 3 atomic building blocks: hubs, links, and satellites. The philosophy here is the absolute separation of concerns. You split a business entity into its keys, its relationships, and its descriptive attributes.
Let's pull these apart piece by piece. Start with the hub. In our banking scenario, what exactly is a hub?
A hub represents a core business concept: a noun, a customer, a product, an employee, a store. But here is the radical departure from traditional modeling. A hub table contains absolutely zero descriptive data.
Wait, none. So a customer hub doesn't have a first name column or a date of birth column?
Nothing. A hub table contains only a few columns. It has a surrogate hash key, the natural business key from the source system, the date that key was first seen by the data warehouse, and a record of which source system provided it. That is it.
I want to really dig into this because it feels so counterintuitive. If I query a customer hub, all I see is a list of IDs and timestamps.
Yes. Think of it like your driver's license number or your passport number. That number uniquely identifies you to the government, but the number itself doesn't tell anyone if you have brown hair or if you need glasses to drive or where you live. It is just the immutable identifier around which everything else revolves.
So in our bank merger, how does the hub handle the SSN versus alphanumeric ID problem?
Beautifully, you create a customer hub. When Bank Alpha sends a record, you load the SSN into the hub, tag it with source, Bank Alpha, and timestamp it. When Bank Beta sends a record, you load the alphanumeric ID into the exact same hub, tag it with source, Bank Beta, and timestamp it.
Wait, you just mix the different types of keys in the same column.
You do, because to the enterprise, both of those strings are valid, immutable identifiers for the concept of a customer. You don't try to resolve them or merge them at this stage. You simply record, with absolute cryptographic certainty, that these identifiers exist in your corporate ecosystem.
Huh.
The hub is incredibly stable because business keys rarely change. Once an ID is in the hub, it's there forever.
Okay, I have my ultra-stable, stripped-down hug of identifiers. But businesses aren't just isolated nouns, right? Customers buy products. Employees manage stores. How do we model the verbs?
That is the role of the link table. Links capture the relationships between hubs. If a customer places an order, you create an order-to-customer link.
And let me guess, keeping with the philosophy, the link table also has no descriptive data.
Exactly right. A link table contains its own unique identifier, the unique identifiers of the hubs it is connecting, a load date, and the record source. It does not contain the total price of the order or the shipping method.
It's just the mathematical connective tissue. It proves that a relationship occurred. Like a purchase receipt from a grocery store. The receipt proves a transaction happened between you and the store at 4:00 p.m., but it doesn't describe the biological makeup of the apples you bought.
That's a great way to visualize it. And structurally, link tables are phenomenal because they inherently handle many-to-many relationships without breaking a sweat.
How so?
Well, in a star schema, if a product can suddenly have multiple suppliers, and a supplier can provide multiple products, you have to build complex, highly engineered bridge tables to resolve the cardinality.
But in a data vault.
You just insert more rows into the existing link table. Product A is linked to supplier X. Tomorrow, product A is also linked to supplier Y. You just add a row. The architecture doesn't care. It absorbs the complexity natively.
All right, I'm tracking with the hubs and the links. But we're building an analytics warehouse here. At some point, the VP of marketing actually needs to know the customer's name, their email address, and their credit score. Where do the adjectives live?
The adjectives, all the descriptive data, live in the satellites. Every satellite table hangs off of either a hub or a link. You might have a customer demographics satellite attached to the customer hub, containing names and dates of birth. You might have a customer credit satellite containing their credit scores.
Why separate them like that? Why not just have one massive satellite for all customer attributes?
Rate of change and source system origin. Your demographic data, your name and date of birth rarely changes, and it probably comes from the CRM. Your credit score changes constantly, and it comes from a third-party financial API.
Oh, I see.
By putting them in separate satellites attached to the same hub, you can update the credit score every hour without constantly duplicating the static demographic data.
And this brings us to the most critical mechanical feature of satellites. How do they handle it when a value actually does change? Say I move from New York to California.
In a traditional transactional database, you run an UPDate statement. You overwrite New York with California. The old data is gone forever. In a data vault, satellites are strictly, religiously insert-only.
Insert only, so you never overwrite anything.
Never. When CRM sends the new California address, the data vault simply inserts a brand new row into the satellite with the California address tagged with a new load timestamp.
Leaving the New York row completely intact, just sitting there with an older timestamp.
Exactly. This is the physics of the data vault. You get complete immutable history as a default feature of the architecture. If an auditor asks where a customer lived 3 years ago on a specific Tuesday, you just query the satellite for the row that was active on that timestamp.
Wow.
It's like a stack of contact cards. When your details change, I don't cross out the old card. I just put a brand new updated card on top of the stack.
Okay, I have to step back and look at the whole picture here. I see the logic. But structurally, it sounds like an absolute nightmare to actually use.
Yeah, it's not easy.
You've taken a single customer profile and shattered it into pieces. You've locked the IDs in a hub drawer, the relationships in a link drawer, and the actual information in multiple different satellite drawers. If I'm an analyst and I just want a simple table of customer name, current address, and last order date, I can't just query one table anymore.
You cannot. Querying a raw data vault directly is an incredibly painful exercise in SQL gymnastics.
Walk me through the pane. What does that SQL query look like?
Okay, so to get that simple profile, you have to select from the customer hub. Then you have to join to the demographic satellite, but you have to write a subquery or a window function to filter for only the most recent timestamp to get the current name.
Right, because of all the history.
Exactly. Then you join to the address satellite, doing the same complex temporal filtering. Then you join to the order link, and then join to the order hub, and join to the order satellite to find the date.
That is easily a 50-line SQL query with 5 massive joins just to answer a basic business question. Why on earth would anyone subject themselves to that level of query complexity?
Because you are paying a complexity tax up front to buy immunity from structural collapse. Yes, it requires more joins. But remember our Jenga tower. When that SaaS vendor adds a brand new shipping field to their API, what happens to your data vault?
Well, the business key hasn't changed, so the hub is fine. The relationships haven't changed, so the links are fine.
Exactly. And your existing satellites remain completely untouched. To accommodate the new field, you simply create one brand new satellite to hold the shipping data and you attach it to the hub. Your existing ETL pipelines keep running. The historical data is safe. You have completely isolated the change.
I see. It's the ultimate modular system. But making this modularity work at enterprise scale required a massive technical leap between Data Vault 1.0 and Data Vault 2.0. And I really want to dig into this because it touches on the raw mechanics of how databases actually compute data. It's the shift from sequence generators to deterministic hash keys.
This is arguably the most brilliant mechanical innovation Dan Lindstedt made when he updated the methodology to 2.0. To appreciate why it's so critical, we have to look at how traditional data warehouses generate primary keys.
Right. In a standard database, if I load a new customer, the database usually just assigns them an auto-incrementing integer. The first customer is ID 1, the next is 2, then 3.
Yes, a sequence generator. It's standard practice, but in a distributed data environment, it creates a catastrophic bottleneck. Let's trace the data pipeline. You are loading your data warehouse overnight. You have a massive batch of new customers and new orders.
Okay, sounds normal.
First, you have to load the customer dimension table because you need the database to assign those sequential IDs, say IDs of 100 through 500.
Right. I need the IDs before I can do anything else.
Exactly. Your order pipeline, which needs to link the order to the customer, is essentially frozen. The database thread processing the orders has to sit there and wait for the thread processing the customers to finish, commit the transaction, and return those new sequential IDs. Only then can the order pipeline resume and write the relationship.
It forces the entire architecture into a single file line. You can't process data in parallel because every downstream table is waiting for the central database to hand out the sequence numbers.
And when you're dealing with terabytes of data or streaming data in real time, you cannot afford to wait in a single file line. Data Vault 2.0 solves this by outlawing sequence generators for primary keys and mandating the use of cryptographic hash keys.
Okay, let's break down the mechanics of a hash key. What is actually happening at the compute level?
A hash function, like MD5 or SHA-1, is a mathematical algorithm. It takes any input, a word, a number, an entire paragraph, and scrambles it into a fixed-length string of characters.
So if I input the business key account 123, the algorithm spits out a seemingly random string of letters and numbers. Seemingly random, but crucially, it is deterministic. Meaning, the string account 123 will always generate the exact same hash output. It doesn't matter what computer is running the algorithm or what time of day it is. The math is universal.
Oh, I think I see where this is going. If the math is universal, I don't need a central database to hand out IDs anymore.
You've got it. Let's look at our pipeline again. You have 50 different compute nodes running in parallel on a cloud platform. Node A is processing the incoming customer data. It sees account 123, runs the MD5 hash, and generates the key. At the exact same microsecond, Node B is processing an order file. It sees a reference to account 123.
Node B doesn't have to talk to Node A. It doesn't have to query the database to ask, hey, what ID did you give account 123? Node B just runs the exact same MD5 math itself, generates the exact same hash key, and writes the link table record immediately. Precisely. They calculate the keys independently. You have completely decoupled the loading process. Hubs, links, and satellites can all be loaded simultaneously in parallel across a distributed cluster. It removes the serialization bottleneck and allows Data Vault to ingest data at blistering speeds.
That is incredibly elegant. It's like giving every single construction worker on a site their own identical set of blueprints and a universal measuring tape, so they never have to wait in line at the foreman's desk to ask where to put a beam.
Is the mathematical key to infinite scalability.
Okay, so we have the building blocks. Hubs for keys, links for relationships, satellites for attributes, all glued together independently using hash keys. But how does this actually manifest in a corporate architecture? You don't just dump all these tables into one big bucket. Modern frameworks dictate a very specific assembly line.
Yes, the architecture is highly layered. We process the data sequentially from left to right. It starts on the far left, extracting from your source systems, and lands first in the staging layer.
The staging layer. In traditional ETL, this is usually where the heavy lifting happens, right? Where we clean up the messy data before letting it into the warehouse.
And that is the exact opposite of what you do in a data vault architecture.
Mm.
In data vault, the staging layer applies only what we call hard business rules.
Define a hard business rule, because to me, a rule is a rule.
A hard business rule is a structural, technical imposition required just to get the data into a database safely. It is mostly data typing. If a source system sends a date as a weird text string, like 2026 Jan 001, a hard rule parses that string and casts it into a proper SQL date format.
Okay, just formatting.
Mostly formatting. The staging layer also calculates those MD5 hash keys we just discussed, and it adds the metadata, load timestamp, and the record source string. But critically, a hard rule never ever alters the actual business meaning or content of the data.
I'm going to challenge this, because I know how bad source data can be. What if that source system sends a date string of February 30th? That is factually, biologically impossible. It's an error. Doesn't a hard rule clean that up?
No. If the staging layer detects February 30th and it can't cast it to a SQL date, it will likely cast it to a default error date or store it as raw text. But it must retain the evidence that the source system provided a fictional date. You do not quietly fix it by changing it to February 28th.
Why not? Why would I want to knowingly pass garbage data downstream into my warehouse?
Because if you fix in staging, you destroy the historical truth. This brings us directly to the next layer on the assembly line, which is the heart of the system, the raw vault.
The raw vault. This is where our hubs, links, and satellites physically live.
Yes, the raw vault is mandatory, and its guiding principle is 100% auditability. It stores the data exactly as it was provided by the source, warts, errors, and all. It never overwrites, and it never judges. It just records.
I see the logic, but I have to push back hard here. If the raw vault is deliberately storing unmodified data, including known bad data, aren't we just building a highly structured, very expensive garbage dump? Executive leadership isn't going to pay millions of dollars for an architecture that happily serves up February 30th on a revenue report.
It's not a garbage dump. It is an evidence locker. And to understand why that distinction matters, you have to look at the legal and compliance realities of massive enterprises. Imagine you are a pharmaceutical company or a major retail bank.
Highly regulated environments.
Extremely regulated. Imagine a regulator audits your firm because a customer was wrongly denied a mortgage 3 years ago. The regulator wants to know exactly why the algorithm made that decision on that specific Tuesday.
Okay, so I need to reconstruct the data as it existed 3 years ago.
Right. Now imagine if, 3 years ago, your staging layer had quietly cleaned a piece of incoming credit data because it looked messy. You applied a business rule to fix it before storing it. When the regulator audits you and you pull the data, you are showing them the cleaned version.
Right.
You are fundamentally incapable of proving what the source system actually transmitted on that day. You have tampered with the evidence.
Oh, I see. If I don't have the raw, ugly truth preserved exactly as it arrived, I have no cryptographically sound lineage.
Exactly. The raw vault is your ultimate system of record. It is unimpeachable. But you are also entirely correct that executives cannot run a business on raw, contradictory evidence. They need clean, actionable metrics.
So how do we bridge that gap? How do we get from the evidence locker to the executive dashboard?
We build the next layer, the business vault.
The business vault. How does this differ from the raw vault?
The business vault sits logically on top of the raw vault. It is an extension of it, built with the same hub, link, and satellite structures, but this is where you apply your soft business rules.
Hard rules were just data types. So what is a soft rule?
Soft rules involve business logic, interpretation, and subjective corporate policy. This is where you calculate derived metrics. For instance, the raw vault might hold every single purchase a customer ever made. The business vault calculates total lifetime value and stores it in a new business satellite.
Okay, derived metrics. What about cleaning the data?
Yes, this is where the cleaning happens. If the raw vault has that impossible February 30th date, a soft business rule in the business vault might filter that record out or explicitly flag it as an anomaly for reporting purposes.
But the crucial difference is that we're applying this cleanup after the raw data is safely locked away in history.
Exactly. And the other massive function of soft rules is resolving conflicts between sources. In a large enterprise, you might have the marketing CRM claiming a customer is active, while the finance billing system claims that same customer is suspended due to non-payment.
Both of those facts are true from the perspective of the source systems, and both are safely recorded in the raw vault.
Right, but the CEO's dashboard can only show one status. So a soft business rule is written. In the event of a conflict, the finance system's status overrides the marketing system. The business vault executes that rule and creates a consolidated single version of the truth satellite.
Okay, this separation is brilliant, but I want to understand the why. Why physically separate the raw vault and the business vault? Why not just apply that finance overrides marketing rule as the data is flowing in and just store the final answer?
Because soft rules business logic are highly volatile. They change all the time.
Give me an example.
Let's say a new chief revenue officer is hired. They look at the dashboard and say, I disagree with this logic. If a customer is suspended in finance but they've engaged with a marketing email in the last 30 days, they are still active to me. The business rule just changed.
Wow. If I had applied the old rule upon ingestion, I would have permanently classified years of historical data based on a rule the company no longer believes in.
And to fix it, you would have to completely reload all your historical data from the source systems, if you even still have it, and reprocess it. It's a massive engineering effort.
But with the separation,
the raw vault remains untouched. It still perfectly records what marketing said and what finance said on every day for the last 5 years. To implement the new CRO's logic, you simply update the code that builds the business vault. You recalculate the business vault views based on the new logic, drawing from the immutable raw vault history.
you can literally change your mind about what historical data means instantly without ever having to reload the data itself. That is incredible agility.
It separates the objective reality of the source systems from the subjective interpretation of the business.
Okay, so we have the staging layer for hard rules, the raw vault for objective history, and the business vault for subjective logic. But we established earlier that querying these vault structures directly requires 50-line SQL nightmares. Where do the business users actually go to build their pie charts?
They go to the final stop on the assembly line, the information delivery layer, usually organized into data marts.
And what does this layer actually look like under the hood?
The irony is, after all our critique of its brittleness earlier, the information delivery layer is almost always built as a Kimball star schema.
Wait, we just spent 20 minutes explaining why star schemas collapse when source systems change, and now we're building one anyway.
We are, but the context changes everything. You aren't building a star schema directly on top of chaotic, mutating source systems. You are building it on top of the highly stable, beautifully historized business vault.
Ah, I see. The data vault acts as a massive shock absorber.
Exactly. When that SaaS vendor adds the new shipping field, it causes a ripple. But the data vault absorbs the ripple. The raw vault catches it in a new satellite. The business vault maps it. And then at your leisure, you simply expose that single new column to your downstream star schema dimension.
Yeah.
The star schema never experiences the structural shock.
So the business analysts get the fast, drag-and-drop simplicity of the star schema they love, and the engineering team gets the indestructible, auditable back end of the data vault. You really are getting the best of both worlds.
You are. But designing that shock absorber, figuring out exactly what should be a hub, what should be a link, and how to structure it, is not an automated process. It requires intense human judgment. Which brings us to the craft of data modeling.
Yes, let's pivot to the human element. We rely heavily on the insights of Neil Strange here, who frames data modeling not just as technical drawing, but as a deeply social skill. And that feels counterintuitive. Most people picture data modelers as hyper-technical engineers locked in a basement with multiple monitors writing DDL scripts. Why is it a social skill?
Because if a modeler acts like an isolated engineer, they inevitably fall into the worst trap in data vault design, which Neil Strange calls the ultimate anti-pattern, bottom-up modeling.
Let's define bottom-up modeling. What does that actually look like in practice?
Bottom-up modeling is when an architect looks at the database tables of a source system, say an on-premise ERP system the company's used for 15 years, and simply reverse engineers it. They copy the vendor's table structures and turn them directly into hubs and links. I mean, I can see the appeal. It's incredibly fast. You just look at the schema the vendor provided, map table A to hub A, table B to hub B, and you're done. Why is that an anti-pattern?
Because you are letting a third-party software vendor dictate the ontological reality of your entire enterprise. Think about a 15-year-old ERP system. It has been patched, hacked, and customized by dozens of developers over the years. It is riddled with technical debt.
It's a Frankenstein monster of code.
Exactly. It has redundant tables, deprecated columns that are still being used for weird workarounds, and highly specific internal terminology. If you model bottom-up, you are immortalizing 15 years of a vendor's technical debt and hard-coding it into your pristine new enterprise warehouse.
There was a fantastic, painful example of this in the literature regarding a CRM system.
Yes, the proposals example. A company had a CRM system that held their legal contracts. But for some bizarre historical reason, the software vendor had named the underlying database table of proposals. So inside the CRM database, it's called proposals. But every human being in the company knows that when they look at that screen, they are looking at a binding contract.
Exactly. The human business users have translated the reality. But if a data modeler works bottom-up, they just look at the database schema. They see a table called proposals, so they blindly create a hub called hub proposal.
And then a year later, a business analyst is trying to write a report on active contracts. They look in the data vault, they don't see a contracts hub, and they assume the data is missing. The modeler perfectly copied the system, but completely failed the business.
That is exactly what happens. So the antidote to this is top-down modeling. You completely ignore the source systems at the beginning of the project.
You ignore the data. How do you model data without looking at the data?
You don't start with data, you start with the business. You get out of the basement, you go upstairs, and you sit in a room with the VP of sales, the head of logistics, and the CFO. You ask them, what are the core concepts of this business? What are the nouns that matter? What are the critical events?
Neil Strange refers to these events as units of work. Let's unpack that term.
A unit of work is a tangible, valuable business process. It's not a database transaction. It's a real-world event. For example, in an insurance company, converting a preliminary quote into a binding, paid policy is a massive unit of work.
Okay, so I sit with the business leaders, and we map out that event. We identify the nouns involved, the customer, the insurance agent, the, quote, the policy, the insured property.
Right. And those nouns agreed upon by the business leaders, using their actual vocabulary, become your hubs. Then you look at the event itself, the act of binding the policy. That event connects the customer to the policy and the agent. That relationship becomes your link table.
And only then, after I have this beautiful business-aligned whiteboard drawing, do I go down into the basement and look at the messy source databases.
Exactly. And your job is to figure out how to map the messy, technical debt-ridden source data into your pristine, business-aligned hubs and links. You force the source systems to conform to the business reality, not the other way around.
I love the philosophy of top-down, but I can imagine sitting in that room with the executives and hitting some incredibly difficult judgment calls. It's not always obvious what a noun is versus what a verb is.
It isn't. And this is the classic hub versus link dilemma that sparks massive debates among data architects. Let's play this out. We are modeling a B2B sales process, and we are looking at a contract. I ask you, as the modeler, is a contract a hub or is it a link?
Well, let's think about it. A contract is fundamentally an agreement connecting two parties. It connects our company, the seller hub, to the client, the buyer hub. Because it's a relationship between two hubs, it must be a link table.
That is a highly logical, completely valid argument. If the contract is simply the event of an agreement taking place, it acts perfectly as a link. But I am the CFO in this meeting, and I say to you, wait a minute. We use that contract number every single month to issue invoices. Our customer support team opens service tickets against specific contract numbers. We amend those contracts, we renew them, they have their own life cycle.
Ah, if other systems are pointing at the contract and attaching their own data to it, it's not just a transient relationship anymore. It has mass. It's an entity in its own right.
Precisely. If a concept is referenced by other processes independently, it cannot just be a link. It has to be elevated to a hub. This is why modeling is a social skill. You cannot answer the hub versus link question by looking at a database schema. You can only answer it by interviewing the humans who run the business and understanding how they use the concept.
It requires immense nuance to find the right level of abstraction. And if you get the abstraction wrong, you can break the entire system. I read about this running joke in the data modeling community about the dangers of extreme abstraction.
Oh, yes, the four tables joke. It's a cautionary tale about taking top-down modeling to an absurd philosophical extreme.
The joke is that a hyper-philosophical data modeler can look at any complex multinational enterprise with millions of products, employees, and transactions and reduce the entire data warehouse down to just four tables.
And those tables are thing, thing type, thing relationship, and relationship type.
Which is technically flawless. A customer is a thing, a product is a thing, a purchase is a thing-thing relationship. It covers the entire universe.
It is structurally bulletproof, but it is practically suicidal.
Let's visualize why it's suicidal. Imagine I'm a business analyst and I just want to write a SQL query to find out how many pairs of shoes we sold in Germany last month. If my database is just those four tables, what does my query look like?
It is a recursive nightmare. You would have to select from the thing table where the thing type is transaction. Then you have to join to the thing relationship table to find the relationship. Then join back to the thing table where the thing type is product and filter for shoes. Then join back to the relationship table to find the location. Then join back to the thing table where the thing type is country and filter for Germany.
I'm exhausted just listening to it. It's a dozen recursive joins against the exact same massive table holding billions of rows.
The database engine would simply melt. A query that should take milliseconds would run for a week and then time out. So extreme abstraction destroys performance.
But the other extreme, being hyperphysical and modeling every tiny detail, is just as bad. The literature highlighted a case study where a modeler tried to build a simple calendar and geography hierarchy.
Yes, a standard business requirement, right? Rolling up days into weeks, months, years, and rolling up stores into districts, regions, and countries.
In a normal warehouse, that's just one or two dimension tables.
But this modeler went hyper-physical with the data vault rules. Instead of keeping it simple, they created a separate hub for day, a hub for week, a hub for month. Then they created link tables connecting day to week, week to month. They did the same for geography. They ended up with 38 separate target tables just to represent a calendar and a map.
38 tables?
And again, if an analyst tries to query that, they're navigating a labyrinth of 38 joins before they even touch the sales data. It was completely unqueryable.
So the modeler is walking a tightrope. If thing is too abstract and 38 calendar tables is too physical, how do you know when you've hit the Goldilocks zone? What is the test for a good model?
The Goldilocks zone is when your hubs map cleanly to the nouns the business leaders actually say out loud in the meeting, and your links map to the verbs they use. If your data model requires a decoder ring for a business user to understand it, it's too abstract. If your model looks exactly like the back end of your Salesforce instance, it's too physical. It has to perfectly reflect the cognitive model of the business.
Finding that Goldilocks zone requires weeks of interviews, intense discipline, and a lot of complex engineering. Why do enterprise organizations voluntarily put themselves through this? We promised to talk about superpowers, and we need to deliver. What is the actual bottom line ROI for paying this complexity tax?
We've touched on them organically, but let's formalize the three massive enterprise superpowers Data Vault unlocks. Superpower number one is absolute change absorption, specifically during mergers and acquisitions.
We discussed the bank merger and how the hub handles the different ID formats, the SSN versus alphanumeric thing. But what about the downstream impact? When that merger happens, what happens to the CEO's existing dashboards?
In a traditional architecture, those dashboards go dark for months, while the engineering team scrambles to integrate the new company's data into the existing models. In a data vault, you add the new Beta Bank keys to the customer hub. You attach brand new satellites to hold Beta Bank's specific attributes. The Alpha Bank data remains completely untouched in its own satellites.
So the old data doesn't move?
It doesn't move, it doesn't change structure. Therefore, the existing reporting views built on top of the alpha data continue to run flawlessly every single day without interruption. You've surgically isolated the change. You integrate the new beta data into the reporting layer incrementally at your own pace without ever breaking the legacy operations.
That is massive for business continuity. Okay, superpower number two, strict auditability and lineage.
This is the feature that makes Data Vault the darling of the healthcare, pharmaceutical, and financial sectors. And to understand why, we have to look at how painful it is to track history in a traditional dimensional model.
Right. If I want to track historical changes in a star schema, I have to build something called a slowly changing dimension, specifically an SCD type 2.
Let's walk through the mechanics of an SCD Type 2 just so you can really feel the pain. Imagine you have a customer row for John Doe. He lives in New York. To track history, your table needs extra metadata columns, a start date, an end date, and an IsActive Boolean flag.
Okay, so John Doe's row says start date, Jan 1, end date. Daxer 31, 9999 is active. True.
Now, John moves to California. To process this update, your ETL code must first query the massive dimension table to find John Doe's currently active row. Then, it must issue a new paid statement. It changes the end date of the New York row to today's date and flips the IsActive flag to false.
And that's a locking operation on the database.
It is. Then the code must issue an insert statement to create a brand new row for John Doe with the California address, a start date of today, an end date of 99999, and the IsActive flag set to true.
I mean, it sounds manageable for one customer.
Now imagine doing that for 10 million customers every single night across 30 different dimension tables, while analysts are simultaneously trying to query those same tables. The locking overhead and the complexity of the ETL code are staggering. If a script fails halfway through, you have overlapping date ranges and your history is completely corrupted.
It's a fragile, highly engineered mechanism, but in a data vault.
In a data vault, history isn't a complex mechanism you have to engineer. It is the fundamental physics of the satellite table. There are no end dates to manage. There are no IsActive flags to flip. There are no UP date statements to lock the database.
Because satellites are strictly insert only.
Exactly. John moves to California. The system simply inserts a new row into the satellite with the new address and a new timestamp. Done. It takes milliseconds. The history is mathematically guaranteed to be accurate. When the healthcare regulator demands to know a patient's exact insurance status on a specific date 5 years ago, you just query the satellite based on the load timestamps. It is a cryptographically solid, unimpeachable audit trail.
Superpower number 2 is unimpeachable auditability. What is the third superpower?
Parallel development. We talked earlier about how hash keys allow computer nodes to process data in parallel. But Data Vault also allows human beings to develop in parallel.
How does the architecture change human workflows?
Let's use a massive retail supply chain example. Imagine a global e-commerce giant dealing with 200 different suppliers. Every single supplier sends their catalog data in a completely different format. Supplier A sends a flat CSV file every night. Supplier B sends a complex nested XML file once a week. Supplier C only pings a REST API when a price changes.
In a traditional architecture, I can't load any of that data into the warehouse until I have cleaned it, standardized it, and forced it to match my central product dimension.
Which means your data engineering team has to build 200 distinct, highly complex ETL pipelines just to get the data through the front door. The engineering team becomes a massive bottleneck. The business is screaming for the new supplier data, but the engineers are stuck writing XML parsers.
And with Data Vault.
With Data Vault, you decouple ingestion from standardization. You spin up 200 raw ingestion pipelines that do almost nothing but generate hash keys and dump the data into 200 different raw vault satellites attached to a central product hub.
Just get it in the door.
Exactly. Because it's a raw vault, it absorbs the data regardless of the format. Now, here is where parallel human development kicks in. The junior data engineers can be tasked with just building those simple ingestion pipes. The senior architects can be working simultaneously on modeling the core hubs and links. The data science team can start querying the raw vault immediately to look for patterns without waiting for it to be cleaned. And the business intelligence team can be working on the business vault rules to eventually standardize it all.
So no one is waiting in line.
Exactly. The modularity of the architecture allows you to scale your development teams horizontally. You could throw 10 teams at a massive integration project, and because they're all just building independent satellites attached to common hubs, they don't step on each other's toes.
It is the ultimate modular construction system. But in the spirit of intellectual honesty, we cannot just sell this as a silver bullet. Modular systems have costs. Space stations are incredible, but they are astronomically expensive to maintain. We need to explore the dark side of the vault. Where does this architecture cause pain?
The pain is real, and it is usually the first thing that shocks teams who adopt this methodology. The most immediate, visceral drawback is table proliferation.
Just the sheer volume of database tables you have to create.
Yes. Let's look at a simple business domain, like customer service. In a traditional star schema, you might model the entire customer service domain with maybe 20 or 30 tables.
Yeah, a few dimensions for agents, customers, and a fact table for the support tickets. Simple.
But in a data vault, Every single core concept is shattered into at least three pieces: the hub, the link, and the satellite. And often it's more. You might have multiple satellites per hub to handle different rates of change. You might need specialized effectivity satellites to track the timeline of relationships.
So what does that 30-table domain look like in a vault?
It easily explodes into 150 or 200 tables.
That is a 5x increase in physical infrastructure.
And it brings a massive administrative burden. Think about security. In the old model, if you wanted to restrict access to sensitive customer data, you put a security policy on one customer table. Now you have to manage role-based access control across a hub and 6 different satellites.
Think about the documentation. The beta dictionary for 200 tables is a full-time job to maintain.
Exactly. The metadata management overhead is significant. But the table proliferation also leads to the second major drawback, which we've touched on: query complexity.
Ah, yes, the 50-line SQL query with 5 joins just to find a customer's address.
Right. Business users and even average data analysts absolutely cannot query the raw vault directly. The cognitive load is too high, and the risk of writing a bad join that creates a Cartesian product and crashes the database is massive.
Which means the data vault is fundamentally useless to the business until you build that final information delivery layer, the star schemas on top of it.
Yes, and building and maintaining that presentation layer is a whole separate development effort. You are building the warehouse twice.
Yeah.
Once for the indestructible backend and once for the consumable front end.
So weighing these superpowers against this administrative pain and query complexity, what are the clear anti-use cases? When should an architect look at Data Vault and say, absolutely not?
It really comes down to scale and volatility. Do not use Data Vault if your company operates on a single, highly stable source system. If you just run one instance of SAP and the schema hasn't changed in 5 years, Data Vault is massive, unwarranted overkill.
What about team size?
If you have a data team of 3 people who just need to get operational reports out the door quickly, avoid Data Vault. The learning curve is steep, and a small team will drown in the table management.
And what if raw query speed on the core warehouse is the absolute most important metric, say, for a high-frequency trading firm?
If you need millisecond latency querying the lowest grain of data, stick to a highly optimized star schema or a flattened wide table. The multi-table joins of a data vault will always carry a compute penalty.
But wait, let's pull on that thread. If the compute penalty of all these joins is so high, how is this methodology exploding in popularity right now? Data volumes are thousands of times larger today than they were when Dan Lindstedt invented this in the 2000s. Shouldn't Data Vault be choking to death on big data?
It would be, if not for a massive paradigm shift in underlying hardware and database engines. We have to talk about the cloud factor.
Okay, how did the cloud save Data Vault?
10 to 15 years ago, you ran your data warehouse on massive, expensive, on-premise relational databases: Oracle, Teradata, SQL Server. These row-based systems were fundamentally constrained by physical disk I/O. If you asked an on-premise database to join 10 massive tables together, the hard drives literally had to spin, read the data row by row, load it into limited RAM, and try to match it. It would bring the system to its knees.
So people avoided normalization just to save the hardware.
Exactly. But modern cloud data platforms, specifically architectures like Snowflake or Databricks running Delta Lake on Parquet files, have completely rewritten the rules of database physics.
Break that down. What makes Snowflake different?
2 things. First, the infinite separation of compute and storage. In the cloud, if a query is too heavy, you don't have to buy a new server. You just instantly spin up a massive cluster of compute nodes, throw them at the query for 10 seconds, and then shut them down.
You can just brute force the join.
I can. But more importantly, these platforms use columnar storage and advanced micropartitioning. When you query a massive satellite table in Snowflake, it doesn't scan the whole table. It knows exactly which micropartitions contain the specific columns and hash keys you need, and it ignores the rest.
So it trims the fat before it even starts processing?
Yes. They are hyper-optimized for complex joins. A 10-table data vault query that would have run for 3 hours on a legacy on-premise system can now run in 6 seconds on a modern cloud warehouse. The cloud made the massive table proliferation of Data Vault computationally viable at enterprise scale.
I hear that, but I have to raise a red flag here. If your solution to bad query design is just, spin up a massive cloud cluster and brute force it, aren't you just trading architectural technical debt for a terrifyingly high monthly cloud bill? Snowflake charges by the compute second.
That is the multi-million-dollar warning.
Yeah.
And you are entirely correct. If you build a data vault poorly, it will become an incinerator for your IT budget.
And this is where Neil Strange's warnings about discipline become critical. He talks about the absolute necessity of staying on a best.
Like skiing, staying on the groomed trail.
Exactly. Data Vault has very strict mathematical rules. Hubs never contain descriptive data, satellites never connect to other satellites, links never contain dates.
What happens if I break a rule? Say I'm an engineer, I'm under a deadline, and I decide to just stick an effectivity date directly into a link table to save myself from building an effectivity satellite. Seems like a clever shortcut. It works for about a month. And then your data volume doubles. Suddenly, the cloud optimizer can't accurately partition that link table anymore because you've mixed relationship keys with temporal data. Your query performance degrades. So what do? You increase your Snowflake warehouse size from large to extra large.
And the monthly bill doubles.
And then it doubles again. Neil Strange compares breaking the standards to driving a car repeatedly into a wall. If you deliberately break the structural physics of the model, you cannot blame the car when it shatters, and your cloud bill bankrupts the department.
So building this requires extreme discipline. You have to follow the rules, manage hundreds of tables, and navigate top-down business politics. How does a team actually execute this without losing their minds?
Execution requires a rigid, phased methodology and a total commitment to automation. If you look at modern implementation guides like the frameworks provided by OvalEdge or Wearscape, they mandate a very specific 5-step pipeline.
Let's walk through the actual implementation journey. Step 1.
Step 1 is plan. This is the top-down modeling phase we discussed. You sit in the boardroom, you identify the units of work, you argue about hives and links, and you define your core business keys. You do not write a single line of SQL.
Okay. Step 2.
Step 2 is build the raw vault. You translate that conceptual model into physical tables. You build the ingestion pipelines from your source systems, you calculate the MD5 hashes, you apply the hard rules, and you start streaming the immutable history into the satellites.
So we have our evidence locker. Step 3.
Step 3 is build the business vault. Now you bring in the data scientists and the analysts. They write the soft rules, resolve the source conflicts, calculate the derived metrics, and store them in business satellites.
Making the data subjective and useful. Step 4.
Step 4 is set up information delivery. You build the star schemas, the dimensional views, and the aggregations on top of the business vault, providing the clean, fast interface for the BI tools like Tableau or Power BI.
And what is the final step?
Step 5 is arguably the most critical for survival. Automate and optimize. And I cannot overstate this, the engineering guides are incredibly aggressive about this point. Manual implementation of a data vault is a death sentence for a data team.
Why is it a death sentence? We have smart engineers that can write SQL?
Because of the scale. Remember the table proliferation. If you have 200 tables, you have to write 200 separate ETL load scripts. And the logic for loading a data vault is highly standardized, but highly repetitive.
Let's picture the code. To load a single satellite, what does the script have to do?
First, the script has to calculate the hash key of the incoming record. Then it has to query the existing satellite to see if that hash key already exists. Then it has to compare the incoming descriptive attributes to the most recent historical record.
To see if anything actually changed.
Right. It has to calculate a hash diff, a hash of all the descriptive columns combined. If the hash diff is identical to the current record, it drops the row. If the hash diff is different, it generates a new load timestamp and executes an insert statement.
And I have to write that exact same boilerplate logic flawlessly 200 times.
Yes. And if a team of expensive software engineers tries to hand code that, they will spend 100% of their time writing boilerplate SQL instead of analyzing data. The syntax errors alone will stall the project for months.
So what is the alternative?
Code generation software. Tools like Wearscape, Studio, or DBT with specialized data vault macros. You feed the tool your conceptual model, you tell it, this is a hub, this is a satellite, and the tool automatically generates the hundreds of thousands of lines of perfectly standardized, optimized SQL code required to build and load the vault.
So the human becomes the architect, and the software acts as the bricklayer.
Exactly. Automation is the make or break factor. If you aren't automating the code generation, you shouldn't be building a data vault.
Okay, if automation handles the coding grunt work, let's talk about the planning phase. Because the elephant in the room of modern technology is generative AI. Neil Strange specifically addressed using GenAI, like ChatGPT or Claude, in the data vault process. Where does it fit?
It's a fascinating application. He notes that GenAI is a phenomenal assistant during that crucial step 1, the top-down modeling phase.
Really? I would think AI would be terrible at top-down modeling because it requires interviewing human executives.
It can't conduct the interview, but it accelerates the preparation dramatically. Say you are building a vault for an industry you don't know, commercial shipping logistics. You can prompt an LLM. I'm modeling a data vault for a maritime shipping company. What are the standard industry units of work? What are the core entities I should consider for hubs?
And the AI instantly spits out. You need hubs for vessels, ports, cargo manifests, customs declarations, and your core events are docking, unloading, and clearing customs.
Exactly. It provides a highly educated rough draft of the conceptual model. It can even draft the initial business glossary definitions for those terms, ensuring you walk into the meeting with the executives armed with a solid baseline.
That is incredibly powerful. But I have to ask the inevitable question. If AI can draft the conceptual model, and tools like Warescape can automatically generate all the underlying SQL code, isn't the role of the human data architect effectively dead? Are we just automating ourselves out of a job?
It is a valid fear, but Neil Strange counters it directly. He argues that human judgment is absolutely irreplaceable for the last mile of modeling.
Why? What can't the AI do?
The AI understands general industry concepts, but it fundamentally lacks the context of your specific, messy, highly political corporate reality.
Paint that picture for me.
The AI doesn't know that your company just acquired a rival, and the two VPs of sales hate each other and refuse to agree on what a closed deal means. The AI doesn't know that the legacy CRM system is structurally broken, and the sales team actually keeps the real revenue numbers in a hidden SharePoint Excel file.
Right. The AI assumes a rational world.
Precisely. The AI assumes data is rational. But enterprise data is a manifestation of human behavior, and humans are irrational. The human data architect provides the empathy, the political negotiation, and the social skill required to get warring departments to agree on a unified business definition. The AI is a brilliant assistant, but the human is the diplomat and the architect.
That is a profoundly reassuring perspective. It really highlights that data architecture isn't just a math problem, it's a human alignment problem. Let's pull back and synthesize this entire journey for you listening as you look at your own corporate ecosystems.
Right. To summarize, the thesis of this deep dive data vault is a methodology designed for survival in chaotic environments. By ruthlessly separating your business keys into hubs, your relationships into links, and your temporal attributes into satellites, you create a modular architecture. It absorbs vendor API changes without breaking. It provides an unimpeachable insert-only historical audit trail. And it allows distributed engineering teams to build the future in parallel without bottlenecks.
It is the ultimate shock absorber for enterprise reality. But as we wrap up, I want to leave you with one final, deeply provocative thought to mull over. This is inspired by the trends noted in modern architecture guides, and it looks toward the very near future of what data even is.
It is a paradigm shift that will make data vault not just a good idea, but a foundational requirement for corporate survival. We are entering the era of synthetic data.
Synthetic data, so data that isn't generated by a real human clicking a real mouse or a real truck dropping off a real package.
Exactly. Data generated by advanced simulations, by digital twins modeling supply chain disruptions, by AI agents conducting thousands of automated customer service interactions.
Estimates suggest that within the next few years, nearly 30% of all data flowing through corporate networks will be completely synthetic. So here is the question you must ask yourself. When your business is running on a massive, indistinguishable mixture of real-world historical facts and AI-generated simulated scenarios, how will you tell the difference?
If you are running a traditional flattened data warehouse where data is constantly overwritten and lineage is an afterthought, you won't be able to.
That is a chilling prospect. Without a fully auditable, cryptographically linked foundation like a data vault, a system that strictly records exactly what system generated what record and at what millisecond, synthetic data will quietly, invisibly drift into your objective reality.
Your executives will be looking at dashboards, making multi-million-dollar capital allocation decisions, entirely unaware that the revenue trend line they are trusting is heavily skewed by a batch of simulated data that an AI agent injected into the pipeline for testing purposes.
Corporate governance becomes impossible. You literally lose your grip on reality. So as everyone rushes to buy the latest large language models and embrace the AI revolution, remember this: AI readiness does not start with the algorithm. It starts with the architecture.
It always comes back to the foundation. If you cannot trace the lineage of a fact, you do not have a fact.
You just have a hallucination on a pie chart. But if you build that foundation correctly, if you embrace the separation of concerns, then when the API breaks or the merger happens or the synthetic data floods the system, you won't be left standing there holding a single block, watching your entire Jenga tower collapse.
You'll just calmly snap a new module into the hub and keep building upward.
Thank you for joining us on this deep dive. Keep asking questions, keep digging deep into the architecture of your reality, and we will see you next time.